You know, I've spent more than 40 years in theoretical physics, and there's one thing that has always haunted me. How can we understand quarks, the weak interaction, the Higgs mechanism, even predict the hydrogen spectrum with 12 decimal places of accuracy, yet be completely unable to predict the personality of a newborn child? In 1964, Murray Gell-Mann named the quark. In 1973, asymptotic freedom was discovered, paving the way to understand how quarks behave more obediently when they are close together. And by 2012, the Higgs boson was finally found at CERN, confirming the mass generation mechanism that the entire community had been waiting for nearly half a century. Yet despite all those glorious triumphs of physics, we still cannot answer one simple question: what kind of person will this child become? And that's when I want you to meet an idea that the scientific community calls emergence. The term appeared as early as 1875 in the work of philosopher George Henry Lewes, and today it is one of the central concepts of complexity science. Emergence says that when many simple elements interact, they can give rise to entirely new properties that cannot be found in any individual element. Look at water. The property of being wet does not exist in Haythorpe or Ord. Or take murmuration. When 10,000 starlings form fluid, graceful shapes in the sky that no mathematician can predict from the motion of a single bird. And if even simple systems like water or flocks of birds can give rise to such new properties, then human beings with billions of cells, trillions of neural connections, and countless social interactions must be the most complex emergent system we have ever known. And when talking about complex systems that emerge beyond predictability, I am reminded of a friend of modern science, Professor Brian Cox. You've probably seen him on TV, a bright face, a gentle British voice, and a passion for the universe strong enough to convince even people who had never cared about physics to look up at the sky. Brian is a particle physicist at the University of Manchester, a member of the Atlas experiment at CERN, one of the two giant detectors that helped discover the Higgs boson in 2012, a scientific triumph watched by the entire world. But what is even more interesting is the way he brings science to the public. In 2013, Brian set a Guinness World Record for the largest physics lecture in the world, with 5,697 people packed into Manchester's MN Arena to hear him talk about the universe. Just think about it. Nearly 6,000 people voluntarily spending their evening listening to a physics lecture. This was no accident. It was the result of a massive wave of popular science that exploded in the 2010s, with the BBC playing an enormous role. The series Wonders of the Universe that Brian presented in 2011 attracted millions of viewers and turned physics, often seen as dry, into an emotional story about our very existence. And you know what fascinates me the most? It's the emergence of such crowds. A single person can be curious, but when thousands come together, they create a kind of collective energy that psychologist Gustave Le Bon described in his 1895 study of crowd psychology, and later quantified in models by Dirk Helbing in 2005. No one in the crowd can single-handedly create that atmosphere. It only appears when they stand side by side, when emotion, curiosity, and awe spread like dominoes. That is emergence in its most beautiful form. Things we cannot predict from a single individual, but that appear when enough people share a moment. And I have to admit, sometimes I feel a little jealous. I once taught a class of 3 students at Caltech. 3. If Guinness gave an award for the physics lecture with the fewest attendees, I would win hands down. But you see, the appeal of science doesn't come from the equations. Even though I love equations, it comes from the story we tell about ourselves in this universe, where we come from, how we are made, and why a system of countless tiny particles can emerge into a thinking being that wonders about itself. And here, once again, is why we need to talk about humans as an emergent system that cannot be predicted from fundamental equations. Sometimes I feel that planets behave far more predictably than first-year students who ask me, "Professor, does an electron really exist?" Our Earth orbits the Sun at an average distance of 149.6 million kilometers so far that if you drove there at 100 kilometers per h, it would take more than 170 years, assuming you didn't burn to ash as you approached the Sun. Light, traveling 300,000 kilometers per second, still takes more than 8 minutes to cover that distance. Saturn, with its mesmerizing rings, first clearly photographed by Voyager 1, 1979, and Voyager 2, 1981, takes 29.4 years to complete one orbit. Every planet, from Mercury racing like an overexcited child to Neptune silently drifting at the cold, dark edge, follows the laws Johannes Kepler wrote down between 1609 and 1619. Kepler had no supercomputers, no satellites, no NASA data. He had only his eyes, a pair of compasses, a notebook, and an almost unbelievable stubbornness. Yet he described planetary orbits with equations so simple that today's high school students can try them and still get results accurate to a few arc seconds. That is what amazes me. The solar system obeys simple rules so obediently. If you know mass, distance, and gravity, you can predict a planet's motion thousands of years into the future. You don't need to know the personality of Mars. It doesn't wake up tomorrow and decide to change its orbit because it feels bored. Yet that very absolute stability only highlights the unruliness of human beings. And to understand why we are so chaotic, we must look at the bigger picture, cosmology. According to data from the Planck collaboration released in 2018, our universe began about 13.8 billion years ago in a hot, dense state smaller than an atom. It wasn't an explosion in the Hollywood sense. There were no bursts of fire, no boom sound. It was simply space expanding itself, a spectacular expansion that physics calls the Big Bang. Since then, the universe has kept expanding, cooling, leaving behind a mixture of components that honestly makes no intuitive sense. Only about 4.9% is ordinary matter, the atoms, electrons, neutrons that make up you, me, morning coffee, and the cars on the road. About 26.8% is dark matter, a mysterious form of matter, never directly observed, and only inferred through its gravitational effects. And the vast majority, 68.3%, is dark energy, something accelerating the expansion of the universe faster and faster. And frankly, no one really understands what it is. But wait, the story gets even more interesting. When you look at large-scale maps of the universe, like data from the Sloan Digital Sky Survey, SDSS, that began in 2000, you see that galaxies are not scattered randomly. Instead, they form a gigantic structure shaped like a network, the cosmic web. The filaments of this web can stretch hundreds of millions of light years long. Sounds abstract, but imagine holding a ruler 1 light year long. 1 light year is already 9.46 trillion kilometers. Now multiply that by hundreds of millions. Yet the universe weaves filaments like that, trillions upon trillions of times, creating a macroscopic spiderweb that spans space. The strange thing is, no one drew the cosmic web. It emerged. Tiny quantum fluctuations during the inflationary epoch, just a tiny fraction of a second after the Big Bang, were stretched to galaxy-sized scales, creating this network. Those minuscule ripples, through time and gravity, emerged into the largest structures in the universe. And this is when I laughed to myself. Planets behave. Neurons don't. If Kepler could describe planetary motion with 3 laws no one has ever written, 3 laws of human behavior, no equation predicts whether today you wake up feeling full of love for life, or tomorrow you feel stressed because your partner forgot to buy milk. Our brain, with 86 billion neurons, each connecting to thousands of synapses, creates a complexity far beyond anything in the solar system. And just as the cosmic web emerged from quantum fluctuations, human beings emerge from countless microscopic interactions that no equation can fully capture. So if the entire universe runs on emergence, and even the largest structures ever to exist cannot be predicted from initial conditions, then expecting that we can predict a human being, a nonlinear, chaotic, continuously changing system, is simply unrealistic. The universe may be humbly simple at planetary scales, but when you go deep enough or wide enough, it teaches you one lesson. The most important things are always emergent, and human beings are the most beautiful proof of that emergence. And if the cosmic web shows us how tiny quantum fluctuations can emerge into gigantic structures spanning hundreds of millions of light years, then your own body is the most spectacular example of how nature turns the small into the large, the simple into the unimaginable. Start with a single cell, a unit so small it requires a microscope to see, yet it contains 20,000 to 25,000 genes and nearly 10 billion protein molecules carrying out millions of chemical reactions every second. Each gene is not a fixed command, but more like a flexible instruction manual. It turns on, turns off, responds to the environment, changes how proteins are made, and thereby affects the behavior of the entire cell. But the truly interesting part is not in any single gene or molecule. It lies in how they interact. Just as you cannot understand a piece of music simply by listing the notes. Now move up a level, the brain. What sits inside your skull is one of the most complex structures in the known universe, a system containing roughly 86 billion neurons. Each neuron connects on average to about 7,000 synapses, meaning the total number of synaptic connections ranges from 600 trillion to about 1 quadrillion, a number so large that even I, who have spent a lifetime working with infinities, have to raise an eyebrow. And imagine every one of those synapses can strengthen, weaken, disappear, or be newly formed, all depending on experience, emotion, hormones, memory, and even tiny random events happening in every millisecond. If the solar system is a predictable dance, then your brain is a chaotic festival where billions of dancers move to their own rhythm, yet still produce a meaningful harmony. Thought. The miracle is that no single neuron knows you are thinking, just as no single water molecule knows it is creating an ocean wave. Thought is emergent. It arises from countless microscopic interactions that no individual neuron can describe. And this leads to one of biology's greatest secrets. You cannot understand consciousness by looking at one neuron. You can only understand it by looking at the simultaneous activity of billions of neurons. This is where complexity grows, exponentially, from molecule to cell, cell to tissue, tissue to brain, brain to mind. At each level, nature creates a new emergent layer that cannot be fully reduced to the level below. It's like climbing a ladder where each rung speaks a different language. Genes speak chemistry, proteins speak biochemistry, cells speak biology, and mind speaks philosophy and emotion. And this emergence can be exquisitely sensitive. A tiny change can make all the difference. Take the serotonin transporter gene, commonly called 5-HTTLPR. This gene controls how serotonin, a neurotransmitter related to mood, is transported in the brain. A small variant in this gene, just a single change in the DNA sequence, can make one person react much more strongly to stress than another. Not because the gene decides their emotions, but because it modulates hundreds of other signaling pathways in the neural network. When signaling changes, thinking changes. When thinking changes, behavior changes. It's hard to believe that a tiny change in a single molecule can affect how you face life. But that is exactly how emergence works. The large is always influenced by the small, yet can never be fully predicted from it. This brings us to a clear conclusion. Human complexity does not come from our chemical Lego pieces, but from how they interact in space and time. The speed at which your brain processes information, hundreds of trillions of signals per second, far exceeds any supercomputer ever built. But the most astonishing thing is, you don't feel the chaos. When you think, you feel coherence. When you love, you feel depth. When you remember, you feel continuity. You never see 86 billion neurons flashing like a city lit up at night. You only see me, and that is the greatest emergence of all. The self, no molecule, contains personality. No gene contains dreams. No neuron contains consciousness. But when they all come together, they create something no single level could predict: a human being. And if this is only the progression from molecule, cell, neuron, mind, just imagine how many more layers of complexity are emerging from everything happening inside you every second. Humans are not merely an emergent system. We are the masters of emergence. And once you see how a small variant in a single gene can change the way a person responds to stress, you begin to realize something fascinating. Everything we experience, thoughts, emotions, choices, arises at a level that the fundamental laws of physics were never designed to describe. This may sound strange, especially since you know physics has done an excellent job describing the microscopic world. We have the Schrödinger equation of 1926, describing the evolution of quantum systems with unmatched precision. 2 years later, in 1928, Paul Dirac gave us the Dirac equation, uniting quantum mechanics with special relativity and predicting the existence of the positron, antimatter, discovered just 4 years later. Those equations are so accurate that, given complete information, they can predict the behavior of electrons, protons, and photons to 12 decimal places. But here is the problem. Those equations tell you absolutely nothing about how a person makes a decision in the supermarket, how they behave in a crowd, or how they change their beliefs over time. That is macro behavior, and it simply does not live in the language of electrons or quantum fields. Want to understand why someone sells their stock at the last minute? Ask Daniel Kahneman and Amos Tversky, the two psychologists who created behavioral economics in 1974, with famous studies like prospect theory, showing that people do not behave according to classical economic logic, but according to an emotional logic full of biases and mental shortcuts. Or remember Solomon Asch's 1951 experiment, when he proved that people can give a wrong answer even when they clearly know the correct one, simply because of group pressure. Tell me, does the Schrödinger equation calculate that? Does the Dirac equation predict who will go along with the crowd even though they know it's wrong? Of course not. No microscopic equation explains emergent macro behavior. The reason is not that physics is weak, but that complexity has grown to the point where microscopic laws are no longer the appropriate language to describe it. To understand this, go back to the most terrifying number in the human body. You are a system of roughly 10,000 molecules, 100 million trillion molecules. If you wanted to simulate this entire system using quantum mechanics, you would need a computer with more states than there are particles in the entire observable universe. Even writing down the quantum state of just 100 electrons would require a data table larger than the number of atoms in the Milky Way galaxy. That is the level of unreal complexity a human possesses. And there is an even more important point. When you have so many elements, The laws governing each individual element become irrelevant. No one describes the viscosity of water by writing equations for every single HLO molecule. No one describes sound waves by simulating every molecular vibration in the air. Likewise, no one describes a human decision by calculating the wave function of every electron in the brain, because when you reach macroscopic scales, the system begins to exhibit new laws, emergent laws. And these new laws cannot be found in the fundamental equations, just as the wetness of water cannot be found in hydrogen and oxygen. So it is utterly meaningless to ask, can I predict a human being from quantum mechanics? Even if you had a supercomputer as powerful as the entire universe, you could not simulate 10,000 molecules interacting in a chaotic, non-linear, ever-changing system influenced by environment, memory, hormones, culture, language, and personal history. And the most ironic part is, even if you could simulate every molecule in a person's brain, you still wouldn't know the meaning of that simulation, just as simulating every pixel in a painting wouldn't tell you it's the Mona Lisa. This is the boundary that fundamental physics cannot cross. The micro laws are beautiful, but macro behavior lives in a different world, where new laws are born, and human beings are one of the most perfect expressions of that emergence. Humans are the problem that even the universe cannot solve from first principles. Even if you want to predict a complex system like a human being, can you measure accurately enough to even begin the problem? And the answer, as you're about to see, is no, absolutely not. This is where chaos theory enters, one of the most beautiful yet brutal discoveries of modern science. In 1963, Edward Lorenz, a meteorologist, discovered that nonlinear systems are extremely sensitive to initial conditions. In his famous experiment, he re-entered weather data with what seemed like a trivially small error, just 0.001 in one variable, but the resulting simulation diverged completely. This led him to coin one of the most famous images in history. A butterfly flapping its wings in Brazil can cause a tornado in Texas. That image isn't really about butterflies or Texas. It's about the fact that in many natural systems, you cannot predict the future unless you know the present with absolute precision. Even a tiny error of a fraction of 1,000 can send the trajectory onto an entirely different path later on. And if this is true for the atmosphere, a system of roughly hentever gas molecules, then it is far truer for the human body. Remember, you consist of approximately 3.7, 2 quarks 10 cells, 37 trillion cells, according to a 2013 study published in Annals of Human Biology. And every one of those cells is not just operating independently. It is constantly interacting with its surroundings, receiving chemical signals, releasing hormones, transmitting protein information, repairing DNA errors, generating ATP energy. But the key point is, they do not operate in sync. There is no central clock making every cell run to the same rhythm. They oscillate, phase lag, speed up, slow down, respond to temperature, nutrition, stress, hormones. All these tiny fluctuations resonate over time, turning the system into a gigantic orchestra where every musician is both highly talented and wildly unpredictable, and there is no conductor. Now try to imagine predicting the future of such a system. You would need to know the exact state of 3.7, 2 quarks 10 cells. Each cell contains billions of molecules, each molecule having position and momentum, governed by quantum mechanics with inherent uncertainty attached. So even if you try to measure, you will always introduce some error. And if that error is on the order of 0.0001 in the Lorenz model, it is enough to make the prediction meaningless within minutes, because your body is not a linear system obeying commands. It is a non-linear system with countless feedback loops. A small change in morning cortisol levels can alter how neurons fire in the hippocampus, which changes how you recall a memory, which changes the emotions you carry through the day, which changes how you interact with others, and ultimately changes even the major logical decisions you make. A change of a few thousandths of a unit in a hormone can lead to a life-altering choice. That is chaos theory in biology. You cannot predict how a stem cell in an embryo will develop, because even a tiny asymmetry in its position at an early moment, an asymmetry no machine can measure, can cause it to differentiate into a different cell type. You cannot predict how the immune system will respond during a flu season, because just 10 million lymphocytes out of 37 trillion cells behaving slightly differently is enough to alter the entire response. And you certainly cannot predict a person's mood in the morning, because even a 0.1% change in synaptic activity is enough to rewrite entire signaling networks. But the most beautiful part of all this is chaos is not a design flaw. It is a feature of life. If every cell in your body behaved like a planet, smoothly, regularly, without deviation, you would never be able to learn, adapt, create, or change. You would be a machine, not a human being. It is precisely this chaos that allows us to grow. It is precisely these microscopic fluctuations that allow thought to emerge. It is precisely this uncertainty, rooted in cellular activity, that makes humans an emergent system full of surprises. And therefore, every attempt to predict the human from first principles runs into an absolute barrier. If you cannot know the exact state of a system at the initial moment, you cannot predict its future state, especially when that system contains 3.7, 2 Koch 10 Kunde cells, each containing billions of molecules, each molecule subject to quantum uncertainty. You cannot measure accurately enough. You cannot compute accurately enough. And even if you could do both, you still couldn't keep up with the speed at which chaos is generated in the body every second. This sensitivity, this absolute dependence on initial conditions, is why predicting human behavior from fundamental physics is not just difficult, it is impossible. You cannot measure that initial state with perfect accuracy, not because our instruments aren't good enough, but because nature does not permit it. This is not a technological limitation. It is a law of the universe. It begins with one of the most famous ideas of the 20th century, the Heisenberg uncertainty principle, announced by Werner Heisenberg in 1927. The principle states that you can never know both the position and momentum of a particle with arbitrary precision simultaneously. If you measure position exactly, you blur momentum. If you measure momentum too precisely, position becomes uncertain. This is not because measuring instruments are clumsy. It is the nature of reality itself. Particles do not have definite position and momentum before measurement. They exist as a probability distribution. That means right from the microscopic foundation, you are already deprived of the ability to gather perfect data to describe the system completely. And if you don't know the exact initial state, you cannot predict the future state, especially in a nonlinear sensitive system like the human body. But let's go deeper. Suppose you decide to ignore quantum mechanics and say, fine, I'll measure all the macroscopic states of the system with advanced technology. It sounds brave, but the universe has another barrier waiting, the Landauer limit, proposed by Rolf Landauer in 1961. This principle states that erasing one bit of information requires a minimum energy expenditure of kT-ln2, where K is Boltzmann's constant, and T is the temperature of the environment. You might think, what does that have to do with measuring a human? But this is the core point. Any system that wants to record information must also erase old information. Every erasure costs energy. That means even a perfect computer running on infinite energy could not store the microscopic state of tentinine molecules in your body, because the energy required to process, store, and erase that information would exceed every resource available in the universe. And that doesn't even account for the speed at which the body changes state. An enzyme can catalyze a reaction in a few picoseconds. A synapse can change strength in milliseconds. Each of your 3.7, 2 corticinine cells is continuously transforming, producing millions of microscopic events every second. To track the system state in real time, you would need to record information faster than the system changes, i.e. more than 10 set events per second. That is far beyond any notion of computation humanity has ever conceived. But even if we imagine an imaginary supercomputer powered by the energy of several stars, you would still hit another barrier. The very act of measuring the system state changes the system. This is not only true for electrons in the double-slit experiment. It is true for cells, proteins, neurons. Any measurement precise enough to give you the microscopic state will disturb the very thing you are trying to observe. Want to measure the exact position of sodium ions in a synapse? The measurement itself alters the electrochemical gradient and disrupts the real signal. Want to measure protein folding states throughout the body? The light or energy of the measurement will alter the configurations of the very molecules you are trying to observe. Nature does not allow you to stand outside and look in. You are part of the process. At this point, let's ask the question. To predict human behavior from first principles, what do you need to know? You need to know the position, velocity, energy, angular momentum, electronic state of every single molecule in the body, roughly 10 quantum particles at one precise instant. But you cannot know both position and momentum of a single particle because of Heisenberg. You cannot store or process that information because of Landauer. You cannot perform the measurement without changing the state because of the observer effect. And you cannot keep up with the rate of change of the system because the body changes faster than any computer can record. So we arrive at a beautiful paradox. Even if you knew every equation in the universe, you still could not supply sufficiently accurate input data to use them. Not because you lack effort, not because the body is too mysterious, but because the universe, through its most fundamental laws, has locked the door. It makes perfect microscopic state collection impossible. And if measuring the microscopic state of the body is already impossible, then when we move to the brain, the control center of every thought, memory, emotion, and choice, you will see that the very concept of prediction almost completely collapses. Because the brain is not merely a complex system. It is a nonlinear emergent system where the smallest things can produce the largest differences, and where subjectivity itself, what you call I, does not reside in any single neuron, but emerges from the vast network of 86 billion neurons, continuously interacting with one another. Start with a simple but staggering fact. The brain processes about 10 synaptic events per second. That means in the time it takes you to finish reading this sentence, trillions upon trillions of events have occurred inside your head, each one potentially capable of changing how you think, how you remember, even how you interpret your entire life. To understand more deeply, you need to look at how the brain restructures itself in real time. fMRI studies over the past 2 decades, particularly from the Allen Institute and MIT, show that the brain is not a fixed circuit board. In just a few milliseconds, brain regions can change connection strengths, form new networks, erase old pathways, activate or go silent, depending on context. A person can change their brain activity pattern simply by thinking differently. For example, when they focus, get distracted, feel anxious, or relax. This functional connectivity is unlike any static system physics has ever described. It is like a city where the entire transportation system is being rebuilt piece by piece every millisecond, while all the vehicles are still moving. If you wanted to simulate it, you wouldn't just need to track 86 billion neurons. You would need to track how they continuously rewrite their own connection map over time. But the most fascinating part is still ahead. In 1983, neurophysiologist Benjamin Libet conducted a controversial but foundational experiment. He asked volunteers to flex a finger whenever they wanted and recorded brain electrical activity. To surprise, the brain began preparing for the action about 300 milliseconds before the participant became consciously aware that they had made the decision. That means your consciousness, The feeling that I am deciding is not the driver of the ship. It is merely informed a little late about what the neural networks have already decided. This is one of the strongest pieces of evidence that consciousness is emergent. It is not an independent entity. It is the result of countless unconscious processes happening simultaneously in the brain. Only when these processes cross a threshold do you feel that you are thinking or acting. This shatters the illusion that human behavior can be precisely deduced from microscopic processes, because your entire subjective experience does not reside in one neuron. It resides in the way billions of neurons coordinate together, and they do not coordinate passively. They self-organize, self-adjust, self-adapt. This is nonlinearity at its most beautiful. A small stimulus can trigger a huge response if it arrives at exactly the right moment in exactly the right network configuration. Conversely, a strong stimulus can be completely ignored if the brain is in a state not ready to process it. The brain does not merely respond. It recreates itself in every moment. That is why you never think the same way twice. Even when you try to recall an old memory, the act of recalling changes the neural network, causing the memory to be overwritten in a new way. This has been proven through reconsolidation studies in the 2000s. Memory is not a static file. It is a dynamic process. What does that mean? It means that you literally are never the same person from one moment to the next. But think deeper. If the brain is a system of 10 postsynaptic events per second, restructuring on millisecond timescales, and consciousness is merely an emergent layer appearing above that entire chaotic activity, then how could any equation possibly predict exactly what you will think, feel, or decide 1 minute from now? And there's more. The very act of observing the brain creates a quantum-like paradox. To measure neural activity, you need to intervene with electrodes, strong magnetic fields, or radio waves. But any measurement, precise enough to show you individual neurons, will alter the very activity you intend to measure. This is exactly like the uncertainty principle. The harder you try to measure, the more you disrupt the system. We are trapped in an impossible loop, cannot measure, cannot model, cannot predict. But even if we ignore all those limits and imagine we had a complete map of the brain, we still could not deduce thought, because the map is not the territory. You can have a perfect snapshot of the entire brain structure, but structure is not activity. Static is not dynamic, and humans are made of dynamics, continuous, relentless dynamics. So the brain becomes the perfect example of nonlinear emergence. From simple elements, complex processes arise, and ultimately something emerges that no equation has ever described: your own lived experience. The brain is at once a chemical machine, a physical phenomenon, and a story. And precisely because of that, it is something no set of microscopic equations can fully predict. And once we see how the brain operates as a nonlinear emergent machine, a self-organizing, self-transforming structure that generates processes no single neuron possesses, we arrive at another widespread misconception, that genes determine who you are. It sounds reasonable. DNA is the blueprint of the body, so surely it must also be the blueprint of personality, abilities, future. But modern science has proven the opposite. When the Human Genome Project was completed in 2003, the world expected a human instruction manual to emerge, a code that would explain everything from height and intelligence to personality. But instead of the 100,000 genes many had expected beforehand, the human genome contains only about 20,000 genes, fewer than rice, about 40,000 genes, and not many more than the roundworm seed, elegans, with roughly 19,000 genes. Think about it. If genes truly determined everything human, why would a worm with almost no complex behavior have roughly the same number of genes as we do? The answer is genes do not determine you. Genes are only the starting point, a toolkit, a set of potential capabilities. The rest comes from the organization of biological networks, from the environment, from experience, and from the very mechanisms that regulate gene expression, a field called epigenetics. The idea that genes are only part of the story appeared early. August Weismann, in the late 19th century, rejected the notion of direct inheritance of acquired characteristics, while Conrad Waddington, in the 1940s, introduced the concept of the epigenetic landscape, a visualization showing that genes are not fixed commands, but pathways that can be activated or blocked depending on developmental conditions. And science continued to prove it. We now know that DNA methylation, histone acetylation, and countless other epigenetic mechanisms can turn genes on or off without changing the DNA sequence. Two people with the exact same genes can have completely different sets of active genes, depending on environment, stress, nutrition, childhood, and even random factors no one can measure. This leads to one of the most beautiful and intuitive pieces of evidence: identical twins. Identical twins share the same genes, identical in every genetic respect. Yet any psychologist will tell you they are often very different. Different tastes, different personalities, different levels of depression, different communication styles, different career inclinations. Decades-long twin studies, such as the Minnesota twin study, show that even people sharing 100% of their DNA still exhibit clear differences in personality, temperament, emotional reactivity, and social behavior. Why? Because genes do not write personality. Genes produce proteins. Proteins build cells. Cells build tissues. Tissues build networks. And networks, especially neural networks, produce emergent behavior. Every psychological trait you think of as innate actually emerges from higher levels of interaction, where genes are only one of hundreds of factors. Take depression as an example. There are gene variants associated with higher risk, but that risk only becomes pronounced when the person carrying the gene experiences severe stress, neglect, or trauma. Same gene, different environment, different outcomes. Or take IQ. Many studies show a genetic component to IQ, but that heritability increases with age. In young children, environment plays a larger role than genes. By adulthood, genetic influence grows stronger. This shows that IQ is not a fixed number from DNA. It is an emergent process shaped by ongoing gene-environment interaction over many years. Even height, a trait that seems purely genetic, depends heavily on childhood nutrition. Average height in Japan increased by more than 10 centimeters in just 60 years, 1950, 2010, not because Japanese genes changed so quickly, but because of better nutrition, healthcare, and living conditions. So what does all this tell us? It tells us that genes do not run alone. Genes are merely the text in the book. How the book is read, interpreted, and lived is determined by countless emergent factors at higher levels. Even within your own body, genes do not operate by command. They operate through regulatory networks where hundreds of proteins modulate one another. Turning off one gene may do nothing, but changing a small environmental factor can alter the activity of the entire network. Genes are like computer hardware components. Personality is like software. You cannot predict the software just by counting the number of components. And this is the most important point. Genes not only do not determine you, they cannot determine you. because humans are an emergent system. Your identity, your personality, memories, fears, desires, does not reside in genes, nor in neurons. It emerges from the way different layers of biology, environment, society, and experience interact with one another. Genes provide potential. Environment selects potential. Experience shapes potential. And you yourself, through countless small decisions every day, build the version that exists. When you understand this, you see why no one can predict a human being from their DNA alone. And that is also why every human being is an emergent story, unique, irreducible to data, and impossible to predict with any fundamental equation. And if genes only lay the foundation, while the emergent brain is what truly creates personality, then there is a third factor that quietly but powerfully shapes human beings: the environment. Not the environment in the sense of clean air or polluted air, but everything you see, hear, touch, taste, feel, experience, and even everything that unconsciously affects you. When I say environment, I mean the enormous stream of information pouring into your brain every day. According to a 2009 study from UC San Diego, the average person takes in about 74 gigabytes of information daily, equivalent to watching 16 HD movies. Of course, most of this information never reaches consciousness. It flows into the brain's unconscious processing systems, where it is filtered, interpreted, and sometimes leaves behind tiny fragments you never become aware of. But the key point is, the brain does not record everything. It retains only a very small portion, the part it deems important, according to its own criteria. This creates an extremely significant consequence. Two people in the exact same objective environment will still produce two completely different subjective versions of reality, because their brains filter, prioritize, and decode information in different ways. The same event, for example, a small childhood criticism, might be forgotten by one child within an hour, but it might stay in another child's mind for life, influencing their self-confidence, communication style, and even career choices later on. That may sound like a psychological description, but neuroscience has proven it with very concrete data. The ACE Adverse Childhood Experiences study, first published in 1998, showed that negative childhood experiences, such as domestic violence, neglect, poverty, parental substance abuse, not only temporarily affect emotions, but actually change the physical structure of the brain. The hippocampus shrinks. The amygdala becomes more sensitive to threats. The prefrontal cortex, the area responsible for rational control, develops less fully. In other words, experience creates anatomy, and new anatomy creates new ways of thinking. That means two children born with the same genes and the same basic biological mechanisms can become completely different people, simply because their environments pushed their brains to develop in two different directions. This is not a metaphor. It is an obvious fact in developmental neuroscience. But the environment does not only affect childhood. It acts continuously throughout life. When you read a book, your neural networks change. When you are criticized, your neural networks change. When you fall in love, your neural networks change. When you lose someone, your neural networks change again. And each change influences how your brain responds to the next thing. This is a non-linear feedback loop. Experience change in neural structure, new neural structure, new way of interpreting, new interpreting, new experience, and it continues. No model can track this loop, let alone predict it. Remember that you take in more than 70 gigabytes of information every day, but the amount you actually store might be only a few megabytes. That means the brain is constantly performing a compilation process. It discards 99.9% of the information to keep only the part it considers important. The problem is, what gets kept does not depend only on the external world. It depends on the structure of your brain itself, a structure already shaped by previous experiences. Do you see the loop yet? Experience shapes the brain. The brain shapes experience. This is a form of emergence that no microscopic equation can fully describe. But there is another factor that makes the environment a gigantic source of randomness. The unpredictability of social interactions. A casual remark from a stranger can change how you think about yourself. A chance opportunity can change your career. A single conversation can make you see the world differently, and you cannot model these interactions because they come from other people, each of whom is a separate emergent system. When you place one emergent system inside an environment of hundreds of other emergent systems, what happens becomes computationally impossible. And when you place all of that under a 74 GB daily stream of information, filtered by nonlinear neural systems, shaped by personal history, influenced by stress, hormones, sleep, experiences, and society, you understand why environment is not a secondary factor, but a vast source of randomness that plays a central role in human unpredictability. Nature does not try to make humans complex. Humans are complex because we live in an environment too information-rich for any system to fully process. And it is precisely within that chaotic sea of information that your personality, preferences, beliefs, fears, and ambitions emerge, arising along paths no one can predict from the beginning. If personal environment alone is enough to make human behavior unpredictable, then when you place an individual inside society, a tangled, dynamic, nonlinear, continuously changing network of relationships, any hope of prediction from first principles immediately vanishes into thin air. Society is not merely a collection of many individuals. It is the highest level emergent system where each person's behavior is shaped by hundreds of forces they do not even recognize. Start with a classic number, the Dunbar number, proposed by anthropologist Robin Dunbar in 1992. Based on analysis of primate brain structures, Dunbar concluded that humans can maintain only about 150 stable social relationships, not 1,000 like a friend list on social media, not 5,000 like the number of people in a stadium, but 150 people whose emotions, contexts, interaction histories, and trustworthiness the brain can track. That means your behavior is shaped by a network of 150 nodes, each node connected to another 150 nodes. And this network changes every day when someone arrives, leaves, gets angry, becomes happy, loves you, hates you, or simply forgets to reply to your message. But that is only the first layer. To understand the complexity of society, you must look at the phenomenon called social contagion. In 1998, Duncan Watts and Stephen Strogatz created the small world network model, showing that behavior can spread through a community in much the same way as a disease model. Only a few random connections are needed for an idea, emotion, or action to spread widely in just a few steps. That means if you are sad, that feeling can affect your close friend, then affect your friend's friend, then reach someone you have never met. Conversely, if someone in your network loses weight, quits smoking, exercises more, or becomes depressed, the likelihood that you change in a similar direction increases significantly. Science has proven this through large studies, such as the Framingham Heart Study, which followed nearly 5,000 people for over 30 years. Every behavior is a ripple spreading through multiple social layers, and you are affected by things you never see. How can you predict a person's behavior if that behavior is the result of hundreds of intersecting social waves every day? And imagine this network does not stand still. It changes over time. A new friend appears, an old relationship ends, a new coworker arrives with a different energy, an idea spreads on the internet, a trend rises and disappears in a week, a video suddenly goes viral worldwide. You live in an ocean of interactions that no one can model. But the most important thing is, society does not only affect you, you also affect society. Every personal decision changes a tiny part of the network, and that change can propagate several degrees. Like a small ripple on water, you are not merely the output of the system. You are part of the equation, and therefore this system of equations never has a closed solution. Let's return to the question. Can you predict the behavior of an individual isolated from society? No, because humans do not exist in isolation. You cannot model someone without modeling the network of 150 people who directly influence them, and the 150 quads 150 people who indirectly influence them, and the entire society that influences them through culture, media, stereotypes, expectations, laws, history, economics. To predict one person, you must predict everyone. You must simulate society. You must simulate the entire culture. You must simulate the economic market, the internet, the history of wars, political trends, artistic movements, random events, and even the emotions of people they have never met, but who influence them through a news article, a movie, or a single comment. Humans are not merely the product of genes plus brain plus environment. Humans are the product of genes. God is brain, God is environment, God is society, where each factor is itself a non-linear system, and society is the most complex emergent layer nature has ever produced. Your behavior does not only reflect you, it reflects your position in a much larger network, and that network, similar to the cosmic web and similar to the synaptic network in the brain, cannot be predicted by any equation derived from fundamental particles. That is why society is the strongest evidence that humans cannot be described from first principles. Not because we lack data, not because we lack models, but because the very nature of society is emergent, a whole infinitely greater than the sum of its parts. Humans can only understand humans through stories, not equations. And that is precisely why human behavior remains a mystery, not only to science, but to each of us. Let's start with economics, a field many people think of as exact science, but in reality is a mirror reflecting the chaos of society. In 1963, mathematician Benoit Mandelbrot analyzed data from the US cotton market and discovered something shocking. Stock markets do not follow the Gaussian distribution that classical economics assumed. Classical economic models require the world to be beautiful, smooth, bell-shaped, with finite variance. But reality is different. Market price fluctuations have fat tails, meaning extreme events occur far more frequently than Gaussian predictions allow. This makes predicting markets almost a hopeless game, because a single small event at one point in the economic network can trigger a global domino effect, just as a stumble in the US subprime mortgage market in 2007 led to the 2008 global financial crisis. This shows collective emergent behavior far exceeds the behavior of individuals, and certainly cannot be reduced to fundamental particles. But economics is only the first layer of superemergence. The second layer, broader and older, is culture. If genes are the biological memory of the individual, then culture is the collective memory of society. Culture does not reside in one person's brain. It resides in the interaction network spanning many generations. It includes language, symbols, storytelling, rituals, art, customs, and countless things none of us invented, but all of us practice every day. From a distance, culture looks like a gigantic neural network where memory is not in individuals, but in the interaction patterns of many people. A single person cannot create culture. Culture emerges from millions of small actions by millions of people over hundreds of years. And this has a very powerful consequence. Culture shapes behavior as strongly as genes or the brain. A child raised in Japan, where culture emphasizes the collective, will develop different emotional responses and thinking patterns than a child raised in American culture, which emphasizes the individual. This remains true even when the two children have the same genes, the same brain structure, and the same biological capabilities. Thus, culture creates a new emergent layer that neurons cannot explain. Try modeling the behavior of an American in 2024 by simulating their 86 billion neurons alone. You will fail immediately because that behavior is also shaped by Hollywood, social media, political history, individualism, economic polarization, collective memory after events, while of which lie outside the individual brain, but directly affect that individual brain. And just when you think it cannot get more complex, you encounter the final emergent layer, ideology. Ideology is not a single idea. It is the product of history, plus media, plus events, plus power structures, plus crowd psychology. It emerges in the true sense. No one invented nationalism, liberalism, or religious fundamentalism. They appeared when countless stories, events, fears, hopes, conflicts, and memories intersected across generations. Ideology has the power to shape collective behavior in ways no individual neuron ever could. No neuron in your brain knows anything about capitalism or conservatism. But the network of experiences molded by family, school, media, national history emerges into powerful beliefs that can lead you to a ballot, a protest, or even war. And the most important thing is you cannot reduce an ideology back to a neuron, just as you cannot reduce a storm back to a single water molecule. When you look at an individual, what you see is not just 86 billion neurons or 20,000 genes. You are looking at the product of a social history stretching thousands of years. How can you model the influence of the Industrial Revolution on a person's thinking, or the influence of the internet on a teenager's self-confidence, or the influence of the Cold War on perceptions of the enemy? These things cannot be written into equations. They are not in DNA, but they shape humans more than anything else. And that is the essence of superemergence, systems too large, too deep, too memory-rich to be reduced to small components. When you place an individual within economics, culture, and ideology, you are placing them in an ocean of emergent laws they cannot see, but which are directing every thought they have. Therefore, predicting humans using fundamental physics is not only wrong, it also ignores the most important emergent layers of human existence. Humans act not because of their electrons, but because of their stories. Once you see that economics, culture, and ideology are all super-emergent layers that no microscopic equation can reach, you will immediately understand why artificial intelligence, no matter how powerful, cannot predict a human in the way many people hope. Because AI, especially large language models, does not learn from physics, does not learn from first principles, does not learn from the laws of the universe. It learns from data sets. It absorbs trillions of characters, millions of books, articles, conversations, and detects patterns. But patterns in data are not laws of nature. They are only blurry snapshots of human behavior in specific social contexts. When you ask an LLM about humans, it does not access genes, neurons, hormones, or brain developmental history. It only accesses the frequency of word appearances in the data it was trained on. This makes AI extremely good at imitating linguistic behavior, but almost incapable of simulating deep biological or psychological behavior that emerges from layers datasets never reach. But even if you gave AI access to biological data, it would still hit an insurmountable wall: the computational complexity of the human brain. Remember that the brain processes about 10 synapses per second. That number is so large that simulating it in real time would require a computing system far beyond anything humanity has ever built. The most powerful commercial GPU today, NVIDIA H100, can reach about 4 teraflops, FP64, or approximately 70 teraflops, FP16. And in tensor core mode, it can reach hundreds of teraflops. But that is still only 10 efter operations per second. hundreds to thousands of times less than the actual activity of the brain. And that does not even address the bigger problem. The brain does not operate solely through computation. It operates through chemistry, synaptic plasticity, electrical oscillations, hormonal signaling, distributed nonlinear networks, structural plasticity, emotion, experience, consciousness integration, none of which GPUs were designed to simulate. Even if you had a supercomputer as powerful as Frontier or Aurora, machines reaching exaflop performance, you still could not fully simulate 10 itares synaptic events per second, because synapses are not operations. They are complex biochemical processes tuned by hundreds of hidden variables that science has never measured with sufficient precision. But then there is an even deeper barrier, the prediction paradox of AGI, implied in Gödel's theorems and Stephen Wolfram's arguments. The core idea is this: a system cannot perfectly simulate a system more complex than itself. The human brain, with 86 billion neurons, 10 itares synapses per second, and thousands of emergent layers from biology to psychology and society, is a system whose possible states vastly exceed any physical computer that can exist. Not only because the number of states is too large, but because those states are nonlinear, unstable, incompletely determined, and governed by self-referential mechanisms that Gödel proved cannot be fully encompassed by any finite set of rules. Moreover, Wolfram showed in A New Kind of Science that even extremely simple systems like cellular automata can exhibit unpredictable and irreducible behavior. When you apply this to humans, an organic cellular automaton, billions of times more complex, predicting behavior becomes not just difficult, but in principle, impossible. And this is the crucial point that prevents AI from predicting humans. AI does not know why you do something. It only knows what others in the data have done. It simulates statistical patterns, not the actual structure of you. An LLM can predict the next sentence you will write, but it cannot predict your life, cannot predict who you will love, what will hurt you, what will heal you, or how you will change after an important conversation. Those things emerge from thousands of layers of personal experience that no dataset captures. And even if you gave AI your entire life history, it still could not simulate future social interactions coming from hundreds of other people, each of whom is an independent emergent system. To predict you, AI would have to simulate the entire society. To simulate society, AI would have to simulate culture. To simulate culture, AI would have to simulate human history. And to simulate human history, AI would have to simulate itself, because it has become part of human society. A system would have to simulate the entire system that contains it. That is the impossible self-referential paradox. Therefore, no matter how powerful AI becomes, no matter how large the dataset, no matter how fast the hardware reaches exaflops, it cannot predict humans in the way that first principles physics once did for electrons. Not because AI is weak, but because humans are too complex for any finite system to simulate from the bottom up. And if artificial intelligence, with all the power of modern computing, still cannot predict human behavior, then step back even further, millions of years ago, to see an even stronger layer of unpredictability: evolution. Because humans do not emerge merely from genes, environment, society, or culture. We emerge from the random history of life itself. When you look at evolution, the first thing you must accept is nature has no blueprint, no long-term goal, no intention to create Homo sapiens. It only has mutation, genetic drift, and natural selection. Three processes that operate continuously but are not directed toward any specific endpoint. A study published in Nature in 2010 estimated that each human carries on average about 130 new gene mutations compared to their parents. That means even if you could perfectly simulate the gene life of the parents, you still could not predict what you would look like, how you would think, or what your health would be like, because 130 new changes have appeared completely at random. Most of these mutations are neutral. Some are beneficial, some are harmful. But the most important point is no one can know in advance which mutation will occur, where at what moment, and how it will interact with the environment in the future to produce new traits. Mutation is only the first layer of randomness. The second layer is genetic drift. In small populations, a completely neutral gene variant can become widespread purely by chance. If, by chance, individuals carrying that variant happen to have more offspring, not because it is better, but purely by circumstance, the variant spreads. Eventually, it can become fixed in the entire species, completely unrelated to any biological advantage. When you think about it this way, you realize that the human genome is the history of millions of random dice rolls, not a linear, predictable process. But the uncertainty does not stop at the gene level. It extends to the species level. Consider the clearest example. No one could have predicted Homo sapiens from Australopithecus 3 million years ago. Imagine a scientist standing in Africa 3 million years ago, looking at Australopithecus afarensis, a small ape-like creature with a brain only 1/3 the size of a modern human brain, living mainly by gathering, not yet using sophisticated tools. Ask that scientist, could this creature invent satellites, write symphonies, build particle accelerators, or debate quantum mechanics? The answer would certainly be no, absolutely not. No mathematical model, no genetic rule, no biological observation could predict that a creature with a 450 cc brain would evolve into Homo sapiens with a 1,300 cc brain, complex language, abstract thinking, and even the capacity to imagine the future. Even if you simulated evolution with complete data from that moment, you still could not predict a climate shift drying out the East African forests, forcing our ancestors onto the savannah standing upright to spot predator, freeing the hand, developing tool, developing communication, increasing social pressure selection for larger brain, formation of culture, formation of language, formation of abstract thought. That is a chain of layer upon layer emergence, and you cannot know the 20th layer in advance if you only know the first. Evolution does not work by filling in the blanks. It is like assembling a puzzle in the dark, where each new piece changes the shape of the picture, and the picture is never finished. The truth is, more species have gone extinct than have ever existed. Over 99% of all species that have ever lived on Earth are gone. If evolution had a goal, it would have failed 99% of the time. But precisely because it has no goal, it was able to produce humans, an emergent system that no one, not even nature itself, could predict. And the most astonishing thing is, the randomness of evolution is not only in the past, it continues in the present. Every generation of children born today carries new mutations that no one in history has ever had. Modern environmental pressures, from technology, urbanization, light pollution, to changes in diet, are creating entirely new conditions that no genome has ever faced before. That means evolution has not stopped. It has only become more complex. So when you ask, can humans be predicted from first principles, you are overlooking the fact that even genes, even the human species, even the entire history of biology cannot predict itself. We are not the product of an equation. We are the product of 13.8 billion years of randomness, selection, interaction, events and emergence, where each layer depends on the previous one in an irreversible way. And this is the deepest reason why humans cannot be compressed into a set of fundamental laws. We are not the inevitable outcome of nature. We are an emergent possibility, one small branch among countless possible evolutionary branches. If you ran the history of life again, the chance of Homo sapiens appearing would be close to zero. Once you see that evolution operates like a layered random machine, where every turning point in life depends on countless unpredictable variables, we return to a question every theoretical physicist has heard. If you knew all the fundamental particles and all the equations of nature, could you deduce humans? My answer, sorry if it disappoints you, is no. And even worse, the question itself is completely meaningless, because what we call the equations of nature actually only describe a tiny fragment of the world, and that fragment sits at the lowest layer. It is not the key that unlocks every emergent layer above. The standard model of particle physics is one of the greatest achievements of 20th century science. It describes the universe with 17 fundamental particles divided into quarks, leptons, bosons, along with the Higgs boson. For the model to work, we must input about 26 constants, numbers no one knows why they have the values they do. Electron mass, strong interaction strength, neutrino mixing angle, Higgs field magnitude. Those constants are like the default settings of the universe, unexplained, only accepted. But even if you knew all of that, the full 17 particles, all 26 constants, all the quantum field equations, you would still only be looking at the lowest layer of reality. And that layer, I remind you, does not describe gravity, does not describe consciousness, does not describe chemistry, does not describe biology, and certainly does not describe humanness. The standard model contains no information about chemical bonds, no laws of thermodynamics, no Darwin, no Freud, no Shakespeare, no stories you tell about yourself. It knows nothing about love, pain, childhood memories, personal motivations, or the confusion of a long sleepless night. It knows nothing because it was not designed to know. The universe does not belittle us. We are simply asking the question at the wrong layer to see the absurdity of deducing humans from quarks. Try this thought experiment. Give someone a pile of solutions to the Schrödinger, Dirac, and Yang, Mills equations, and expect them to deduce the structure of DNA from that. That is already impossible. DNA emerges from chemistry, and chemistry emerges from physics, but cannot be reduced backward by pure mathematics. Now ask them to deduce cells from DNA. Again, impossible. From cells to organs, from organs to the nervous system, from the nervous system to consciousness, from consciousness to personality, from personality to behavior. At each step in that chain, nature creates a new emergent layer, and each layer cannot be fully reduced to the layer below, just as you cannot guess the shape of a snowflake from the molecular structure of water alone, or predict flock behavior from the model of a single bird. But let's return to the standard model and look straight at its clearest limitation. It does not include gravity. Gravity, the force that keeps us standing upright, keeps the moon orbiting Earth, keeps galaxies from flying apart, is not included in the fundamental particle physics model. We currently have general relativity describing gravity as the curvature of space-time, but that theory does not reconcile with quantum mechanics. The two pillars of modern physics stand side by side, but do not speak to each other. If gravity itself does not appear in the fundamental equations of particle physics, How can you possibly use those equations to deduce a system as highly emergent as a human being? Even chemistry, the field describing the combination of electrons, protons, neutrons, is not directly produced by the Standard Model. It emerges through the layer of orbital descriptions, binding energies, Pauli exclusion principle. Biology emerges from chemistry, enzyme reactions, DNA replication, gene expression mechanisms, endocrine feedback loops, immune systems. Finally, psychology and society emerge from biology. And this is the layer where no fundamental particle knows it exists. An electron knows nothing about friendship. A quark knows nothing about curiosity. A photon understands nothing about decisions. And the Standard Model cannot predict any of those things, not because it is wrong, but because it was not built to do that. It explains the bricks. It does not explain the building. Every correct theory has its domain of correctness. The Standard Model is correct at the microscopic scale. But humans exist at an emergent scale, consisting of millions of interacting layers. Hoping to deduce humans from quarks is like hoping to deduce the Mona Lisa from the microscopic equations of oil paint molecules. You can simulate every atom in the painting, but you will never see the smile. And that is precisely why, although physics gives us a beautiful foundation describing the microscopic world, it can never describe the world of stories, memories, desires, and emotions that we call humanness. The Standard Model can tell you what the universe is built from, but it cannot tell you who humans are. And that is exactly why predicting humans from quarks is not just absurd. It is a reminder that the beauty of nature does not lie in compressing everything into one equation, but in the countless emergent layers those equations allow to bloom. If the Standard Model has already shown that reducing humans back to quarks is meaningless right from the physical structure, then when you add a more subtle quantum element, entanglement or quantum entanglement, you will see that nature does not merely make reduction difficult, it makes it impossible in principle. Because entanglement is not simply two particles connected to each other. It is a process in which information is spread across the entire system to the point that you no longer know where the original information is. One of the most profound discoveries of quantum mechanics is entanglement entropy, a measure of how much information is mixed in a quantum system. The paradox is, entanglement entropy tends to increase over time, even though the underlying quantum laws are time reversible. That means you can write very beautiful, very compact, very precise quantum evolution equations. But if you try to reverse the process to find the initial state, you almost always fail because the information has been dispersed into the system in a way that cannot be recovered locally. This is precisely why thermodynamics still holds, even though the microscopic foundation is quantum and reversible. Entanglement destroys the ability to reverse. Now extend this to reality. Your brain is not an isolated system. Every second, billions of molecules in your body interact with the surrounding environment, exchanging energy, photons, phonons, electrons. Every neuron emits tiny electromagnetic signals that are absorbed by the environment. Every molecule in your body continuously falls into quantum interacting states with water, proteins, air, heat. That means you are continuously entangled with the environment, from the molecular level to the thermodynamic level. The consequence is that all microscopic information about the initial state of any part of your body becomes no longer belonging to you. It is shared with the environment, spreads outward, dissolves into the mixture we call reality. To predict you, an AI or any model would have to separate you from the environment. But that is impossible. Humans are never in an isolated state. You are entangled with everything you touch, everything you hear, every photon hitting your skin, every molecule you breathe in. There is no individual you. There is a larger system of which you are only a part. This becomes even more interesting in 2013 when Juan Maldacena and Leonard Susskind proposed the famous EPR conjecture. They suggested that two seemingly unrelated ideas in physics, Einstein, Rosen bridges and Einstein, Podolsky, Rosen entanglement, might actually be the same phenomenon, seen from two different perspectives. In other words, entanglement might be geometry, and wormholes might be a manifestation of entanglement. When two particles are entangled, we can think of a tiny quantum tunnel existing between them, not for interstellar travel, but showing that information between the two particles cannot be separated. Whether true or not, this conjecture gives us a beautiful picture. Entanglement is invisible tunnels, connecting every element of the universe, making information belong not to any individual part, but to the whole system. When you think your neurons interact with millions of ions, billions of water molecules, countless thermal vibrations, step by step, every signal, every tiny change becomes entangled with the environment's entropy. All information that might be useful for predicting future behavior slips off the edge of the system and dissolves into the universe. Want to reverse engineer your behavior with equations? You would have to reverse engineer the entire surrounding environment at every moment. That means you would have to reverse engineer the entire universe. Not only is your body entangled with the environment, humans are also entangled with each other through language, memory, emotion, culture, and social networks. When you talk to someone, you exchange information, change their mental state, and they change you in return. Every conversation is an entanglement event at the psychological and social level. Therefore, an individual's behavior does not emerge only from their brain. It emerges from the entangled network of countless interactions. You cannot assume that an individual is an independent unit. You cannot separate someone from their history, from the people they met, from the experiences that shaped them, from the stories they heard, or from the memories they created. Humans are not collections of particles. We are patterns of interaction among countless factors, and that pattern is entangled in a way that cannot be untangled. This is exactly what makes predicting humans from first principles impossible. You cannot measure the initial state because of Heisenberg. You cannot store the information because of Landauer. You cannot simulate the brain because of nonlinearity. You cannot simulate society because of emergence. And finally, you cannot reverse the system because entanglement destroys local information over time. You are not a separate system to be modeled. You are a part of the universe, entangling itself. Predicting humans with fundamental physics is no different from trying to peel a wave away from the ocean to study it. The moment you separate it, it is no longer itself. Humans only truly exist in the entangled state with everything around them. And that is why each of us is a mystery that the universe never intended to allow to be solved by equations. If entanglement was already enough to shatter every attempt to reduce humans back to microscopic states, then when you touch on a bolder concept of modern physics, emergent space-time arising from quantum interactions, you will see that the problem is not just that we cannot model humans. It is that the very stage we stand on, space and time, is also not the fundamental layer of reality. This idea, which sounds more philosophical than physical, actually comes from very concrete research on quantum networks and information structure. One of the important turning points occurred in 2012 when Brian Swingle, then a young graduate student at MIT, proposed that tensor networks, a mathematical structure used to describe complex quantum states, could be understood as toy models of curved space-time. That is, instead of treating space-time as the background in which particles exist, you can do the reverse. Treat entanglement as the foundation, and space-time as the emergent geometric outcome of entanglement patterns. This idea became even more compelling when it was discovered that certain tensor networks, such as mirror, produce structures identical to the adze geometry used in string theory. This is no coincidence. It suggests that geometry is not an input to the universe. It is an output. Space may only be a surface woven from deeper entanglement threads. If entanglement changes, geometry changes. If geometry changes, space-time changes. And if space-time itself is emergent, then distance, time, motion, all the things we call physical context are also higher level manifestations of quantum laws we have not yet fully seen. This may seem far removed from the story of humans, but it actually leads to an extremely powerful conclusion. If even space-time is emergent, then predicting humans from first principles is an impossible task, because first principles are no longer what we thought they were. In the years that followed, this concept was pushed further with the ER=EPR conjecture I mentioned earlier. If entanglement is truly equivalent to tiny Einstein, Rosen tunnels, then geometry of space-time, the distances, curvatures, spatial structures, is simply the way the universe manifests deeper information relationships. From there, many quantum physicists began asking, if entanglement creates space, what creates time? The answer is still debated, but many models suggest that time may emerge from the increase of entanglement entropy, meaning time itself is the flow of information becoming entangled among parts of the system. When entanglement increases, time flows. When entanglement stops, time freezes. This opens a staggering perspective. We do not live in space-time. We live in an information network from which space-time itself emerges. Space and time are not the foundation for human existence. They are emergent results from the very quantum interactions that constitute everything, including us. And here let me be clear. If even space-time is emergent, how can you possibly hope to predict the human? When you try to simulate the human brain, you do not just have to simulate neurons. You do not just have to simulate proteins. You do not just have to simulate molecules. You also have to simulate how those molecules interact with quantum fields. Then how those quantum fields create entanglement structures. Then how those entanglement structures emerge into space-time geometry. And finally, you have to simulate how the brain interacts back and forth with the environment within a space-time geometry that itself changes over time because of deeper entanglement. In other words, to predict a human, you must predict the entire universe, because the physical context in which humans exist is not a static foundation, but an emergent layer from the very interactions you are trying to simulate. You cannot model humans without modeling the emergent space-time conditions around them. And you cannot model that without modeling global entanglement. This is the paradox of every predictive effort. The deeper you try to go backward, the more you see there is no stable bottom layer to stand on. There is no fixed foundation on which to write equations describing humans. The universe has no bottom. It has a network. Therefore, when you say predict humans from physics, you are asking for something impossible. Fundamental physics sits at the microscopic layer. Humans emerge at the macroscopic layer. Space-time emerges at a layer deeper than microscopic. And all these layers influence each other in ways that cannot be reversed. Humans do not live inside space-time. Humans emerge together with space-time. And that makes us fundamentally unpredictable, because even the context in which we exist is not ultimate reality. If you want to find the reason why predicting humans is impossible, you do not need to look only at the highest layers of psychology or culture. Sometimes just looking at the structure of space-time is enough to see that the universe never intended to make humans into an equation with a solution. And if space-time itself is emergent, meaning even the deepest physical foundation of reality is not stable in the way we once thought, then try looking back at humans, a creature sitting atop dozens of emergent layers, operating inside a world where every single photon, every molecule of air, every social touch can alter the direction of a life. When you understand that, you will see why chaos, nonlinear chaos, is not a separate layer in nature, but something that runs through every single layer of human functioning, from biology to psychology to society. And in a system like that, where chaos in one layer becomes the initial condition for chaos in the next layer, predicting an individual becomes not just difficult, but completely impossible. Start with chaos in biology. Your body is an orchestra of millions of simultaneous microscopic chemical processes, and just one small fluctuation can change the melody of the entire concert. Hormones, those messenger molecules in the body, oscillate by the minute, even by the second. Your cortisol level can change just because you caught an uncomfortable glance from a stranger. Serotonin fluctuates when you think of a sad memory. Dopamine rises just because you received a sweet text message. These oscillations are not linear. They do not follow a regular formula. They are like thermal fluctuations in a small region of the atmosphere, irregular, hard to predict, and strongly amplifying. But that is only the first layer. The second layer is even more intense. Your microbiome, the ecosystem of microorganisms living in your body, consisting of about 100 trillion bacteria. That number is many times larger than the number of human cells you have. And the funny or terrifying thing is that the microbiome changes every day according to diet, sleep, stress levels, environment, medications, even the weather. A small shift in the ratio of gut bacteria has been proven to affect anxiety, depression, reward-seeking behavior, and emotional regulation. That means a random change in some unconscious bacterial population in your gut can make you want to go for a walk today instead of staying home, or vice versa. From gene cell microbiome, hormone neuron, mood behavior, layer upon layer of chaos stacks on top of chaos. But now, let's move to the psychological level, where chaos becomes more familiar with your everyday experience. Human mood oscillates according to a cycle called the circadian rhythm, lasting about 24 hours and governed by hormones, body temperature, light, and the biological clock. But the circadian rhythm is never perfectly stable. One night of insomnia throws the whole system off. A morning with too much coffee throws it off a little more. A blood sugar spike when you skip a meal makes neurons react more intensely to negative stimuli. A sudden memory surges when you hear a song, causing adrenaline to spike in just a few seconds. All of these things happen continuously, creating new initial conditions for your behavior every minute. So how do you predict a person today while their serotonin, dopamine, and cortisol levels are oscillating like ocean waves? But then there is the third layer, chaos in society. In the age of social media, an individual is not just affected by the 150 closest relationships of Dunbar's number. They are affected by thousands of social data points every day. A tweet, a short video, a provocative comment, a viral fake news story, or an inspiring post. All of these can change the mood of an entire community in a few hours. Information spreads in a non-linear pattern, just like a disease. An individual on social media can receive 10,000 influences from people they have never met. And worse, social media amplifies the already chaotic features of human psychology. Bad news spreads faster than good news. Fear spreads faster than reason. Anger spreads faster than understanding. An unexpected event on the other side of the planet can change your emotions just seconds later. And all these factors, fluctuating microbiome, fluctuating hormones, fluctuating circadian rhythm, fluctuating social media, continuously stack on top of each other, amplify each other, creating a multi-layered chaos system. No model can predict behavior in such a system, because to predict the next step you would need to measure the initial state of every single layer. You would need to know the person's hormone concentrations every second, the microbiome composition every minute, which memories are currently active in their neural network, what information they just accidentally read, which emotions they are trying to suppress, their social state that day, the economic, cultural, and historical context they are living in. Just one factor being wrong, and your prediction veers off course. But since all these factors are always fluctuating, accurate prediction is impossible right from the starting point. The universe does not merely love chaos. It uses chaos as raw material to create life. This is especially true for humans. Chaos in biology makes every second in your body a new combination. Chaos in psychology makes every moment in consciousness a different emotional configuration. Chaos in society makes every day face an immeasurable stream of influence. And when all these layers of chaos mix together, you get what physics calls a multi-layered, non-linear, chaotic system. The kind of system that even the most powerful supercomputer cannot predict accurately even 1 hour ahead. If someone claims they can predict humans using fundamental physics, they have not understood chaos. If they claim they can predict using AI, they have not understood the social layer. If they claim they can predict using neuroscience, they have not understood the microbiome. Humans are not the sum of those layers. Humans are the chaotic superposition of every layer, emerging in a way no model can reduce. And amid all that chaos, from the microbiome, fluctuating by the minute, hormones shifting by the hour, emotions swinging with the circadian rhythm, to society fluctuating with every scroll, you might think predicting humans is completely impossible. And yes, predicting an individual is impossible. But that does not mean we cannot predict anything. In fact, science has long shown that while each individual is an unsolvable maze, collective behavior follows statistical patterns that are astonishingly stable. This is the most beautiful paradox of behavioral science. You cannot predict one person, but you can predict the crowd. Start with one of the oldest principles, the Weber-Fechner law, formulated in the 19th century. This law states that human perception does not increase linearly with stimulus, but logarithmically. This explains why a person easily notices a change in light intensity in a dark room, but barely notices the same change in a bright room. It explains why a light pinch in a sensitive area hurts more than a hard pinch in a less innervated area. And more importantly, it shows that sensation, something that seems chaotic and deeply subjective, actually obeys very clear statistical laws. When it comes to economic decisions or choice behavior, no one has had greater influence than Daniel Kahneman and Amos Tversky. Through prospect theory in 1979, they showed that humans tend to fear losses more than they desire gains, and that we make decisions not based on absolute value, but on changes relative to a reference point. For example, losing $100 hurts more than the pleasure of gaining $100. This behavior is nonlinear, full of biases, full of emotion, but it can be predicted at the statistical level. That means even though you cannot guess what specific person A will do in a situation, you can guess what proportion of people in that group will do it. This is also true in physics. Many people mistakenly think physics is the science of certainty, but in reality, since 1926, the entire field has been based on probability. Quantum mechanics, the foundation of all modern technology, does not predict the exact position of an electron. It only predicts the probability of where the electron will appear. And strangely, that probability is accurate to the point that experiments must use 12 decimal places to verify it. That means the universe does not tell you the particle is here. It only tells you the particle has a 72% chance here, 28% there. You do not know the individual case, but you know the pattern. And that pattern is enough to build lasers, computer chips, MRI machines, GPS, and everything else. When you bring this probabilistic thinking into human science, you see something similar. We cannot predict every single action, but we can predict behavioral trends. For example, you cannot predict which specific person will share fake news, but you can predict the spread rate of fake news. You cannot predict who will buy a product, but you can predict the consumption habits of a group. You cannot predict who will feel sad when, but you can predict seasonal emotional fluctuation levels. You cannot predict who will vote for which candidate, but you can predict political shift waves on the scale of millions of people. Even the most chaotic systems have their own statistical laws. The temperature of a gas, the motion of molecules, diffusion, entropy, all of these are unpredictable at the individual particle level, but perfectly predictable when you consider billions of particles. Humans are the same. Each individual is chaotic, but the collective of humans is stable to a frightening degree. You can predict divorce rates by year, crime rates by region, social media usage levels by age group, average size of close friend circles, frequency of smiles in a conversation. Even things that seem very free, such as fashion styles, music trends, internet memes, follow power law curves, meaning a few become extremely popular while most fail quickly. This is not constraint. This is emergence. It says that when individuals interact in a large system, collective behavior forms laws. And this brings us to the most important conclusion of this section. Humans cannot be predicted individually, but trends can be predicted. The universe gives us chaos at the microscopic layer, but order at the macroscopic layer. Humans are the same. Each of us is a variable, but society is an equation. You may not know what I will do tomorrow, but you can know the behavioral trends of a person from my generation, my culture, my environment. This does not diminish individual value. On the contrary, it highlights the beauty of emergence, freedom at the individual level, law at the collective level. And once we understand that we can only predict statistical patterns of behavior and not individual people, we reach the crystallized conclusion of this entire journey. Why, based on everything we know about physics, biology, psychology, and society, is predicting a human from first principles impossible? Not because we are not smart enough, not because technology is not powerful enough, but because the very nature of humans is constructed in a way that makes absolute prediction a forbidden thing in the universe. And that reason is not just one, but 7 layers stacked on top of each other, each layer alone sufficient to break predictability. But nature decided to play harder by placing all 7 layers on the same system. Let's go through each layer to see the full picture at the end. Reason 1, emergence, the arising. This is the foundation of everything we have said. The properties of a system do not lie in its components. Wetness does not lie in water molecules. Flock behavior does not lie in one bird. Economics does not lie in one individual's behavior. And thought does not lie in one neuron. Everything important about humans emerges from the interaction of billions of elements: genes, cells, synapses, neural networks, psychology, society, culture, ideology. Every time we move up a layer, nature gives birth to a new set of laws that cannot be fully reduced backward. So right from the first layer, predicting humans from their constituent parts is already impossible. Reason 2, nonlinearity. Not every change is proportional to its cause. A small change in hormones can alter your emotions for an entire day. A small social signal can reverse the behavior of an entire community. A small stimulus in the neural network at exactly the right moment can lead to a completely different decision. The brain has 86 billion neurons, each capable of amplifying or suppressing signals, making the system a gigantic nonlinear feedback machine. In a nonlinear system, identical inputs do not produce identical outputs. So how can you predict the future if even a perfect copy of you under similar conditions might not make the same decision as you? Reason 3, chaos. Sensitivity to initial conditions makes any complex system quickly become unpredictable. An error as small as 0.0001 in the input data is enough to lead to completely different outcomes. As Edward Lorenz proved in 1963, humans contain 3.7 2-quater 10-coin cells, each containing billions of molecules. Just one molecule behaving slightly differently, one calcium ion entering a synapse a few microseconds early, one hormone molecule secreted a few parts per billion seconds late, is enough to rewrite the outcome of the entire neural network and therefore rewrite behavior. Chaos is not a flaw in humans. It is the raw material that allows life to operate, and it guarantees that every action you take contains an element of uncertainty. Reason 4, measurement impossibility. Even if we wanted to predict, we cannot measure the initial state of the system accurately. Heisenberg's uncertainty principle ensures we can never know both position and momentum of a particle exactly. Landauer ensures we cannot store or process infinite information because the energy cost of erasing one bit scales with KTLN2, and any measurement precise enough to describe molecules in the brain destroys the very state you want to measure. That means the input data needed to predict you cannot be obtained, even in principle. No data, no model, no prediction. Reason 5, environmental randomness. Every day you are exposed to 74 GB of information. Every day you meet new people, hear new sentences, perform small actions you do not remember, but your brain still records part of. Childhood experiences have been proven, a study, 1998, to change the physical structure of the brain for life. Your microbiome changes with every meal. Hormones change with every emotion. A casual remark can also change the direction of your life. No environment repeats exactly. No experience recreates itself. No stream of information flows the same way twice. A human is the sum of all the environments they have ever encountered, and no environment can be predicted. Reason 6, evolutionary randomness. The human species carries on average 130 new gene mutations per generation. There is no way to know which mutation will occur, where, when, and how it will interact with the environment. Australopithecus, 3 million years ago, could not predict Homo sapiens. A small climate change, drying out forests in East Africa, rewrote the entire future of the species. Evolution has no goal. It only has randomness plus selection. And because it has no goal, it also cannot predict an individual. A product of evolution also cannot be predicted. Reason 7, entanglement, quantum entanglement that destroys local information. Entanglement entropy increases over time, spreading initial information across the universe in a way that cannot be recovered locally. ER equals sign. EPR shows that entanglement is the geometry of space-time. That means you are not only entangled with your own body, but also with the environment, with the people you have met, with the light you have seen, with the world you have touched. You are not an isolated system. You are part of the cosmic network. To predict you, one must predict that entire network. To predict that network, one must predict the entire universe, and that is impossible. Putting it all together, humans cannot be predicted because these 7 layers of impossibility stack on top of each other. Emergence ensures you cannot reduce from micro to macro. Nonlinearity ensures small signals can become large outcomes. Chaos ensures every model breaks down quickly. Measurement impossibility ensures we cannot know initial conditions. Environmental randomness ensures no experience is ever recreated. Evolutionary randomness ensures the species itself emerges from chance. Entanglement ensures local information cannot be recovered. When you stack these 7 layers together, you do not just create a hard-to-predict system. You create a system that the universe has designed to resist every attempt at prediction. And that system is you, a human being, not a physics problem, not a mathematical sequence, not AI data, but a multi-layered living emergent system that cannot be compressed into any equation. And because of all those reasons, emergence, nonlinearity, chaos, measurement impossibility, environmental randomness, evolutionary randomness, entanglement. When we reach the end of this journey, we are not just talking about the unpredictability of humans. We are talking about the wondrous nature of your very existence. Because if we trace backward from the highest layer, you, the person reading these lines, down through each layer, we find a story that cannot be simulated, cannot be rewritten, cannot be predicted from any equation. You are built from quarks, fundamental particles that feel nothing, know nothing, except vibrating according to quantum fields. From quarks emerge protons and neutrons. From them emerge atoms. From atoms emerge molecules. From molecules emerge proteins, DNA, enzymes. From trillions upon trillions of biochemical interactions emerge cells. Then from those 3.7, 2 quarks 10 quark cells, following laws not born from any gene, emerge tissues, organs, the nervous system. And within that nervous system, among 86 billion neurons, exchanging signals, 10 quark times per second, emerges a network. No one designed it. It is never fixed, constantly restructuring every millisecond. From that network emerges thought. From thought emerges consciousness. From consciousness emerges personality. From personality emerges behavior. From behavior emerges society, culture, history, and finally, you. No layer in that chain can be fully deduced from the layer below. No layer can be fully described by an equation. No layer exists in isolation. Each requires complex, chaotic, random interactions among billions of elements to arise. When you realize you are the product of hundreds of emergent layers, you also realize that your existence is a miracle no science can summarize in words. Physics describes the foundational bricks. Biology describes complex structures. Psychology describes subjective experiences. Sociology describes collective interactions. But only you are the place where all those layers meet. And precisely because of that intersection, you cannot be reduced from any single layer. You cannot be predicted by the standard model. Because the standard model contains no chemistry, no biology, no consciousness. You cannot be predicted by neuroscience, because neuroscience contains no personal stories, no culture, no social randomness. You cannot be predicted by psychology, because psychology contains no microscopic hormones, no microbiome chaos, no quantum uncertainty. You cannot be predicted by sociology, because sociology contains no neurons, no genes, no evolution. You cannot be predicted by physics, biology, psychology, or sociology alone. You transcend every single layer model. And that is why you are an emergent structure, so beautiful. It is hard to believe a structure that from a distance looks like a single individual, but from close up is an entire miniature universe operating, vibrating, growing, changing every moment. You are the result of 13.8 billion years of interaction, randomness, selection, quantum entanglement, biochemistry, learning and storytelling. You are the universe's emergent answer to the question, what happens if we combine quarks with enough time? But the story does not end there, because every human is not only the result of the past. Every human continues to emerge every day. Every new memory rewrites neural networks. Every conversation opens a new space of meaning. Every social shock, every moment of happiness, every failure, every success becomes a piece that creates tomorrow's you, a version that even today's you cannot predict. And this is the most beautiful thing about the entire story. Humans transcend the predictive power of physics, not because we are special in a supernatural way, but because we emerge in a natural way, according to the very laws that created the universe. Unpredictability is not a weakness. It is proof that you are not a machine. You are a story, a phenomenon, a possibility that will never repeat in the entire history of the universe. And so when you wonder what you are doing in this vast world, remember that you are the highest emergent layer nature has ever produced, at least up to this point in the universe. You are not bound by any equation, any orbit, or any quark. You were born from chaos, but you also create your own order. You were shaped by randomness, but you also have the power to create meaning. You are where the universe experiments with becoming aware of itself. And if one human has already exceeded the predictive power of physics, then I have only one final question, and I hope it will stay with you long after you close this story. If we creatures emergent from quarks are already so complex that we cannot be predicted, then how many other things in the universe are still waiting to emerge that we have absolutely no idea about? If you enjoyed this journey of exploration, please subscribe so you don't miss the next science stories. See you in the next lecture, where the universe always has many more surprises waiting to be told.